All right, this is a video for geometry on the area of regular polygons. We'll start off with an introduction and do a few formulas or definitions, and then we'll definitely get into some solved examples. So first of all, let's just remind ourselves what a regular polygon is. A regular polygon is a polygon that is both equilateral, meaning all sides are congruent, as well as equiangular. Okay, and classic definition of a regular polygon, or classic example, is a square. A square has all 90-degree angles and all congruent sides. But here you can see a picture of a regular hexagon where all 6 sides are congruent, and additionally all 6 interior angles are going to be congruent. Okay, so that's what we're going to be working with today. We're going to be looking for a formula to determine the area of a regular polygon. Okay. A couple definitions first, couple more definitions first. First, I want to talk about the radius of a regular polygon. The radius is the line segment that goes from the center to the vertex. Okay. And this is similar but slightly different from the radius of a circle. The radius of a circle goes from the center just to the perimeter, just to the edge of a circle. But here it goes from the center to a vertex. And that's in contrast to what we call the apothem, which goes from the center to the midpoint of a side. Okay, so I'll highlight the apothem here in red. So that's the apothem right there. It goes from the center to the midpoint of a side. It's going to be perpendicular to the side as well, just due to the symmetry that we find in regular polygons. That's the apothem. All right, before we even get to the formula for finding the area of a regular polygon, I want to do a little bit of practice with finding angles. So here we have a regular pentagon, and we're looking for 3 different angles, okay? And there are a couple ways of doing this. One way you could do this, which I think is a little bit harder and I won't pursue, but I'll just remind you of, is we could find the interior angle of a regular pentagon by using the n-2 times 180 formula and then dividing by the number of sides. And that would certainly work. I think it's actually easier to simply think of this angle as being a big 360-degree angle and then simply divide by the number of sides to get angle 1 first. Okay, so angle 1 is going to be 360 divided by 5. I'm choosing 5 because that's the number of sides we're working with. And that is 72, I think. Yep, 72 degrees. And then from angle 1, we can get angle 2, which is going to be half of angle 1. Okay? That apothem in red is going to divide that central angle, angle 1, in half. And so angle 2 is going to be 36 degrees. And then angle 3 we can get by working with a little right triangle. It's going to be 180 minus the 90 and minus the 36 that we found for angle 2. Okay? And that's going to end up being 54 degrees. Okay? So this is going to be really useful as we go through some of the work, knowing particularly what angle 3 is. And I hope you can maybe look forward a little bit or have a little foresight here. If we know the side length of a regular polygon, then it would be easy for us to get that length right there, but just by dividing the side length in 2. And then if we know angle 3, we could use trigonometry to figure out the apothem of the regular polygon, and we could find the area of that triangle then. Okay, so that's going to be useful. Just finding these angles is going to be useful. Okay, let's get the actual area here, and I'm not going to derive it for you right now, although just do know that it really comes just from the finding the area of a triangle and then thinking about how many triangles we have. Okay, so let's think about the area of this orange or yellow triangle that's highlighted here. It's 1/2 base times height, and then we have many of those identical congruent triangles distributed around the center, around that regular polygon, and we could find the area of the whole thing. So that's where the formula comes from, but here is the actual formula. Area is 1/2 times A times P. Little a is the apothem. And so that, to be clear, is not the radius. So the radius is this right here The apothem is labeled A in the figure. P is the perimeter. And I hope you can see that the perimeter could also be found by taking the length of one side times the number of sides. Okay? So often you're given just the length of one side and how many sides we have, but sometimes you'll be given the entire perimeter. Okay, so area is 1/2 times A times P. Let's go ahead and apply it. So we have a regular decagon. Side length is 8, and the apothem is 12.3. So you don't need to draw a picture here, although you could. Sometimes what I do is I just draw a piece, a rough sketch, a piece of the regular polygon, not necessarily to scale or anything. And that I get the side length as being 8 and the apothem being 12.3. No trigonometry needed, no formula, no finding angles needed here. We'll just use the formula. A decagon has 10 sides, so you need to know that. So let's find the perimeter first. The perimeter around the whole thing is going to be the side length times the number of sides, which is 80. And we can just find the area from there. 1/2 times the apothem times 80. And plug that through our calculator. We get an area of 492 square units. Okay, just simply using the formula. Area is 1/2 AP. We're going to do a couple more complex problems in a second, but first I just want to remind you of how we can find pieces of special right triangles. And these triangles, more specifically, are 45, 45, 90 triangles, or 30, 60, 90 triangles. Okay, and so for the 45, 45, 90 triangle is if we know the legs are x, the hypotenuse is just √2 times x. And that applies for any scaled up or scaled down version of a 45, 45, 90 triangle. The hypotenuse is just √2 times the leg length, and that just comes from the Pythagorean theorem. For a 30, 60, 90 triangle, if we know the short leg, we can get the long leg by multiplying the short leg by √3. We can get the hypotenuse by just doubling the short leg. The way I remember this is I think of this 30, 60, 90 triangle as being half of an equilateral triangle. And so this would be x down here as well. And so therefore it makes sense why each of the sides of this equilateral triangle would be 2x. So that's where that 2x comes from right there. And then the x √3 just comes from the Pythagorean theorem. All right, so let's apply some of that. Here we have a regular hexagon whose side length is 3. So this is a little bit harder. I'm going to draw a rough sketch of a regular hexagon. I'm not going to worry too much about it being perfectly to scale. And I don't think you need to as well. So rough sketch of a regular hexagon, side length is 3. And I always like to draw one of these little triangles, label the apothem, and then half of the side length would be 1.5. Our challenge here, though, is to find the apothem. Okay? So hopefully you can tell that this, let me draw another one of these little triangles in here. This would be 360 divided by 6. So that would be a 60-degree angle. Okay? Each of these triangles would have 60-degree central angles, meaning that this angle up here would be 30. So we do have a 30, 60, 90 triangle that we're working with. Let's zoom in on that a little bit and see if we can do some work with that. Okay, so we have a 60 here, we have a 1.5 base, and we're wondering what the apothem would be. Okay, I hope you can remember from before that the hypotenuse would be double the short leg, so this would be 3 as well. In fact, each of these triangles that are distributed around the center would be equilateral triangles in this case, just because it's a regular hexagon. But let's find A. A would be 1.5 times the square root of 3. Okay, and we could get a decimal approximation for that, but it's nice to keep things exact right now. So we can use our formula. Let's actually find the perimeter first. We have a hexagon with a side length of 3. So 3 millimeters each side, 6 total sides. So we have a perimeter of 18 millimeters. So that's important as well. And then let's just plug it all into our formula here. Our area is 1/2 times the apothem, which is 1.5 root 3 times 18, the perimeter. Okay, I am going to keep the root 3 by itself. I'm looking for an exact answer. So really what I'm going to do is 1/2 times 1.5 times 18, and all of that times the square root of 3. And so I get our final area is 13.5 times the square root of 3, and that would be in square millimeters. And if we wanted to get a decimal approximation, we could just find the square root of 3 as a decimal, multiply by 13.5, and round appropriately from there. All right, let's extend it to a circle. And I hope you can see maybe that the radius and the apothem, as we get more and more sides on a regular polygon, the radius and the apothem approach each other in length, okay? And then once we have infinite sides to a regular polygon, that's called a circle, the radius and the apothem would be equivalent. So we could call this the apothem of a circle. We could also call this the radius of a circle, okay? I want you to remember that the circumference of a circle, also known as the perimeter, right, is 2 times pi times r, okay? So let's use our formula for the area of a regular polygon to really figure out if we could find the area of a circle, okay? So the area of a regular polygon is 1/2 times a times p, and let's plug in some of the stuff that we know, okay? We just talked about how the apothem, as our circle gets, or as our regular polygon gets more and more sides and approaches a circle, the apothem approaches the radius, and the perimeter is the same as the circumference, which is 2 pi r. Let's do some simplifying. 1/2 times 2, those multiply together to give us a 1. And so our final, so those essentially cancel out. Our final formula for area is pi r squared, which we already should be familiar with. We got that by just applying the formula for the area of a regular polygon. All right, so we got through it. We actually found the area of a circle. That was pretty cool. And that's a good place to stop right there.